Hey everyone, and welcome to the second video of the Year 11 Specialist course. This video is going to be going over circle properties and proofs. I've divided this circle properties and proofs kind of unit into two parts. This is part one, in which I'm going to be introducing each of the theorems that you need to use for your circle proofs, circle geometry proofs. And the second video is going to be going over examples where you have to kind of merge your understanding of several different theorems in order to prove a certain geometric result. So I do need to give a forewarning that this video is going to be relatively dry. I'm just going to be basically listing each of the circle of theorems that you need, going over a couple of worked examples. Some of them are self-explanatory, so I won't go over worked examples there. Yeah, so that'll be the purpose of this video. So going over the unit outline, there are several different circle theorems. From memory, I think there were about 10. I might be wrong. There might be 12. Okay, I'm not too sure. But there are a certain number of circle properties and proofs that you need to memorize and that you need to sort of write in your circle proof, geometry proof in order to get full marks, to demonstrate your understanding of each of the theorems. So knowing these circle theorems is really important to doing well in the circle proofs unit. As I mentioned, this video might be a little bit dry, so if you feel on top of the circle theorems already, you can skip forward into the part 2 where I go over worked examples of merging understanding of several different theorems in order to prove a certain geometric result. Let's get straight into the video for now though. Okay, so the first circle theorem I'm going to go over is the angle at the center and angle at the circumference. And if you look at the scars of bullet points here, you can see that corresponds to this point 1.1.7. And so the size of the angle at the center subtended by an arc of a circle is twice the size of the angle at the circumference subtended by the same arc. And what an arc is it's a section of a circle, or more specifically a section of the circumference of a circle. And in this case, the arc is referred to as this bit here, okay? So if I have an angle at the center here, I'll refer to this as 2 theta. And if I have an angle at the circumference of the circle subtended by that same arc, so if the arc forms this angle here, if I'm extending those lines out, this angle here will be half of the angle at the center subtended by the same arc. And so when you're using your circle proof, what you need to do and mention, if you're trying to find, for example, you don't know this angle here, what you're going to need to do is mention that it's, first of all, identify that it's 2 theta, and then your rationalization or justification in your proof needs to be along the lines of the size of the angle at the center subtended by an arc of a circle is twice the size of the angle at the circumference subtended by the same arc, which is an absolute mouthful, but it is something that you need to have memorized and down pat so you can write it down as your justification in each step of your geometric proof. Okay? The reason I've introduced this first is that a lot of the other circle theorems actually follow on naturally from that. Okay? So if I have here, and I consider an angle here, I consider another angle here, okay, then these two angles will be equal to each other. And this kind of makes sense because they will be half of the angle at the center, okay? And each of these are both subtended by the same arc, and if they're both half of the center, then they have to be equal to each other. And so this corresponds to 1.1.8. Angles at the circumference of a circle subtended by the same arc are equal. Okay? So this is the sort of description you want to put when you're providing your justification in your geometric proofs. As one example, if I have something like this here, and I have another subtended by the same arc, and let's say this is 30 degrees, then that means this angle must also be 30 degrees. Okay? If I have an angle here at the center, and this is 40 degrees, and I have an angle at the circumference subtended by the same arc, that means this angle must be 20 degrees, half of the angle at the center subtended by the same arc. Okay, so those are points 1.1.7 and 1.8. Okay. Now, the next thing I want to go over is that chords of equal length subtend equal angles at the center. So if I have my center here, and a chord is this bit here, all right, then if I draw this line here, like that, and I have another chord that is of the same length. So this here is my chord, this is also a chord. If these chords are of the same length, then this angle at the center will be the same. Okay, so if this angle, this chord here and this chord are the same length, then the angles at the center are equal. And conversely, if the angles at the center are equal, that means that the chords subtending them are of equal length. And by extension as well, if the arcs are of the same length, then the angles at the center will also be of the same length. Okay, so if I have, for example, here an angle at the center, and let's say my chord is like this, okay, and let's say this is 30 degrees, this is theta, this is 5 centimeters, and this is also 5 centimeters, then that must mean, because these chords are of equal length, the angles will be equal, and therefore theta must be equal to 30 degrees. Okay, so this is kind of a two-way, sort of an equivalent sort of statement. Chords of equal length subtend equal angles at the center, and conversely, chords that subtend equal angles at the center will be of equal length. Okay? Alright, so this next one I'm going to be going over is the angle in a semicircle is a right angle, which is this first one. Now the reason I've skipped over that and gone straight to 1.1.7 and 1.1.8 instead is because 1.1.6 is a natural consequence of the theorem in 1.1.7. Okay, so if I consider my angle at the center here, and I consider my angle in a semicircle, and I consider this angle here, that is 90 degrees. Okay, the angle in a semicircle is a right angle. So when you're providing your justification in a circle theorem and you want to say that this is 90 degrees, the reason why it's 90 degrees is because the angle in a semicircle is a right angle. And the reason why this is the case is, if you notice here, this is an angle at the center subtended by this arc. And this is an angle at the circumference subtended by the same arc. Okay? So if I consider my angle here, that's 180 degrees, that must mean that the angle at the circumference must be half of that, and therefore it's 90 degrees. So the angle in a semicircle is a right angle is a natural consequence of the size of the angle at the center subtended by an arc of a circle is twice the size of the angle at the circumference subtended by the same arc. Okay? So that's 90 degrees here. Now the other theorem I have included here, and which actually isn't included in the SCARSA syllabus here, is the radius-tangent theorem. And you can just refer to this as the radius-tangent theorem when you are providing your justification in your proof. So the radius-tangent theorem says if I have a tangent here, and it makes that one point of intersection with the circle there, and I have my radius of my circle down to that point on the tangent, down to that point of intersection of the tangent, then this angle must also be 90 degrees. Okay, so the angle formed by a tangent and a radius to the point of intersection of the tangent with the circle will always be 90 degrees. Okay, so I've grouped these two together because they kind of both involve right angles. That's the main reason there. All right. So this next one I am going to go over is the chord multiplication and the tangent chord multiplication theorems. So those are kind of these points here and here. Okay. So when two chords of a circle, so a chord is any line that we draw from one point of a circle to another point of a circle, and another chord like this. So if we have something like this, then let's say we'll just call this A, B, C, D, E. Okay. When two chords of a circle intersect, the product of the lengths of the intervals on one chord equals the product of the lengths of the intervals on the other chord. Okay. So AC and BD are both chords of this circle. And what theorem 1.1.12 tells us is that AE times EC is equal to BE times ED. Okay? So this is what that theorem 1.1.12 tells us. And so if I am trying to provide the justification for why this is the case, what I need to do is I need to spit out exactly these words in my justification of my proof. or something that makes it very clear that that is the proof, or that that is the theorem that we're referring to. Okay? This next one is the secant-tangent theorem, I refer to it as. It might be a little bit easier to remember that way, but when you're providing your justification for your proof, you want to write out the entire theorem as it's given in the Sadler syllabus. So in this case, I draw a tangent, okay, and I draw a secant to this circle. So this is a secant to the circle, and so this is referred to as a secant, and this is referred to as a tangent because it has one point of intersection. A secant is essentially a chord that has the line extended out of the circle. I'll refer to this point of intersection M. This is my point T. This is my point A. And this is my point B. And so as you can see in my secant-tangent sort of theorem here, what the secant-tangent theorem tells me is that AM times BM is equal to TM squared. Okay? So if I give an example of my secant-tangent theorem here, so I draw myself a tangent like this and a secant like this. Okay? And let's say that this point here, I have, this is, well, it's not great here, and this is this entire length here. Okay, it's 8. Let's just assume that that's to scale. And let's say I want to find what this length is. What this length will be is x squared is equal to 8 times 2. Okay, because of my secant-tangent theorem. And so x squared is equal to 16, and so x is equal to 4. We reject minus 4 because a length cannot be negative, right? If we have a chord, intersecting chords theorem, I'll refer to that as the intersecting chords theorem, but you know kind of what I'm talking about. I'm talking about that point 1.1.12. If I have the intersecting chords theorem and I have 3 and 4 and I have 2 over here, then I know, and let's say I want to find y here, 2y is equal to 3 times 4, 2y is equal to 12, and so y will be equal to 6. And so that's an example of my intersecting chords theorem, where this is an example of my secant-tangent theorem. Okay? Now the final circle proof you need to go over is that of cyclic quadrilaterals. And what a cyclic quadrilateral is it's a quadrilateral that has each of its corners at the circumference of a circle. So I'm drawing a cyclic quadrilateral right now. Just get that. And so I'll make it a bit odd. So a cyclic quadrilateral, a cyclic quadrilateral will have its corners at the circumference of a circle. So that's not greatly drawn, but you get what I mean. So let's say this is A, B, C, D. And what the cyclic quadrilateral sort of theorem says is that the opposite angles will be supplementary to one another. So if this is equal to theta, then this is equal to 180 minus theta. And if this is alpha, then this is equal to 180 minus alpha. Okay? And conversely to that, if the opposite angles of a quadrilateral are supplementary, that means they must be cyclic. So a cyclic quadrilateral, something being a cyclic quadrilateral, is equivalent to the angles, opposite angles are supplementary. Okay? So if you see a quadrilateral whose corners are at the circumference of the circle, you will know that the opposite angles will be supplementary. And conversely, if you see a quadrilateral and the opposite angles are supplementary, that means you must be able to construct a circle such that the circle's circumference passes through all of the corners of that quadrilateral. Okay? So if I have something like this, a square, for example, is by definition a cyclic quadrilateral because all angles in a square are 90 degrees. 90 plus 90 is 180 degrees. 90 plus 90, 180 degrees. Okay? So therefore, all squares are cyclic quadrilaterals. That means we are able to draw a circle that passes through all corners of that square, and so the square is a cyclic quadrilateral. If alternatively we have something like this, and we have a quadrilateral, and each of the corners of that quadrilateral, okay, lie on the circumference of the circle. So we have something like this. All right, and let's say this is 30 degrees, and I want to find what that angle is. 30 plus that angle will always be equal to 180 degrees, okay? It will be supplementary, so theta in this case is equal to 150 degrees, okay? Alternatively here, if I have 45 degrees and I want to find an angle alpha here, alpha plus 45 degrees will by definition be equal to 180 degrees. It will be supplementary, and therefore alpha is equal to 135 degrees. Okay, so these are two examples of using that property of cyclic quadrilaterals to determine undefined angles. Okay, now the final theorem I'm going to go over is the alternate segment theorem. What the alternate segment theorem is, that's supposed to be a tangent there, by the way, sorry. So this is a triangle that has its vertices at the circumference of the circle. So if this is theta here, okay, then this angle here will also be theta. This is what the alternate segment theorem says. And so this is a relatively short one that you can write in your justification, okay? So these angles will be equal, is what the alternate segment theorem says. And so that's a relatively short one you need to do. So for example, if I say I have a tangent here, all right, and that should have a point of intersection. I've just drawn it very poorly, as usual. So if this case here is 30 degrees, then this will also be equal to 30 degrees, is what the alternate segment theorem says. Okay, so all of these circle properties and theorems are the ones that you need to memorize, as well as what's not mentioned here is the radius tangent theorem. And that's the one I went over earlier. And if you look at the timestamps, you should be able to see where I identify it. I've included that in the description below, and I think it should be timestamped in the video too. So I think that takes us to 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So there's 9 theorems in total. So it's not too bad. There are some converses. I talked about the cyclic quadrilaterals, kind of has a equivalent statement sort of vibe going. The other one that also has that sort of equivalent statement vibe going is the equal chords subtend equal angles, and equal angles at the center subtend equal chords. So kind of you could kind of think about that as being 11 circle theorems, but really it's just 2 equivalent statements, if that makes sense. So that is everything for circle theorems, and in the next video I'm going to go over applications, so using several of those circle theorems to prove certain geometric results. Okay, so I'll see you in that next one, which hopefully will be uploaded in 2-ish days. Yeah, I'll try to get around to that. So thank you for watching this one, and I'll see you in the next video. Bye, guys.